All right, so the plan for today to start from where we left last Tuesday and then learn about acceleration and the motion graphs. All right, so this is where we stopped the other day, I guess. All right, so if you remember, we learned about the distance, then the displacement, speed and velocity. So from under there, we learn about quantities like scalar quantities and the vector quantities. So scalar quantities does have just a number and a unit. So some value and a unit. And then in vectors, we have a number, a magnitude number, and then a unit and a direction. So it's very important to have directions on the velocity, right? So we learn about like how to in vectors. So velocity is a vector, so it's always we need a direction to the velocity. Last Tuesday we practiced like how to calculate the distance, how to calculate the displacement, then the speed and the velocity. So we still need to learn about like a different method to calculate the velocity and then acceleration. So here, if you were given with a graph, so those who are taking the lab class, you know, like we are using graph as a technique to calculate unknown things, right? So in I think one or two labs we use graphing, but in the next few labs, we will be using graph techniques to calculate some unknown values. So anyway, it's good to learn about graph. It doesn't matter what is your major, because in anything you will be reading data, right? So sometimes people are using tables to organize data, but most commonly we are using graphs, right? So various graphs. So this is an example of a scatter graph. So you see like there are dots, then there's a orange color line, that's a fit line. So that's fitting the data. It's not just connecting data, but we're drawing a best fit line that's go distributed among the 3 data points. So here, let's read what is the X and Y coordinates are. So here on the vertical axis, we see meters. That means it's measuring a distance or a displacement, right? And on the x-axis, we see the time. So on the horizontal axis, we have time, okay? So it's a graph of displacement and the time, okay? So it's a graph of displacement versus time. And you see from there, we can read the displacement. So let's say I want to calculate the velocity using this graph, because this is a displacement versus time graph. So if you look at the rise here, so rise means how much it's went in the displacement side, right? So rise over here, what is the displacement of the object? So this object moved from A to C. So the total displacement is from 20 to 80 meters. So we call this as the rise of the graph. So the graph rises from A to C. So the rise of the graph is 80 minus 20. So basically you need to know like how to read the graph. Then this is the run. So the run is the time difference. So in order this object to rise by 80 minus 20, which is 60, this much time has been taken. So this is the run of this graph. So we can calculate the velocity, right? So velocity is the displacement over time. So here displacement from A to C is whatever the rise of the graph, and then divided by the time it has taken. So that is the run of the graph. So rise over run. That's basically the slope of the graph, right? So even though you don't give with a lot of information in words, we can directly use the graph and calculate the velocity. So basically velocity will be 80 minus 20 divided by the time. I'm not sure whether you can see the x-axis from on my screen, because I see this is covering. All right. So from that way, we can calculate the slope of the graph. So the slope of the graph is 2 meters per second. Now, remember, the unit's also important, right? So it's meters per second. Here, meters divided by second. So the units for velocity is meters per second. So the slope of the line is the value of average velocity. So the straight line indicates constant velocity. See, this is a displacement versus time graph, and we see a straight line. So it's continuously increasing its position over the time. So this is a constant velocity graph, a graph of an object that's moving with a constant velocity. Okay. Anyway, so by using a graph, you can calculate the velocity as well. or you can use the equation. Now, when we are dealing with these motions, we really want to pay attention to the direction, as I mentioned, right? So in generally, we are using an arrow to indicate what is the positive direction is. So here in this picture, I have 0 position over here. I'm really referring to a number line. So here's the number line 0. And then I use this arrow to represent, like saying this is the positive side. And then here I'm using, again, the same picture. So I have the 0 position over here. This side is the positive numbers. But look at the location of the car. So the car is over here on this side. And here in the second picture, car is on this side. So basically, the car location is in the negative side. So the displaced or the distance from the 0 to the car's location is negative, right? So anyway, if you want to say the position of the car over in the first picture is negative because it stays in the negative side of the number line. Then over here, the car is in the positive side of the number line, so it is a positive location. Yeah. Then, do you see something that overlapped, and can you see the bottom of the PowerPoint slide?
No, it's covering it.
It's covering, yeah. Okay. Why is that?
Actually, the one that you sent on Canvas does not have the same background.
Oh, maybe that's the problem.
Maybe if you change the design.
Okay. Now you can see it, right?
Yeah.
Yeah. Okay, nice. Because I created PowerPoint slides, like separate PowerPoint slides, and uploaded to the Canvas. Then I combine all three to present. Otherwise, I have to switch between the PowerPoint slides. Anyway, maybe that's the reason. All right, so we good up to this point. Now, remember that the positive direction is only a convention. Like we can change our definition, right? So we can say, oh, this way is positive in one point, but according to our use, we can say, oh, this way is the positive. So it is really convention. So I have an ability that I can switch the positive direction instead of keeping it to the right. So here, as in this blue background, I change the direction to this side and say that is the positive direction. But from this indication, the arrow indication tells me that it is the direction. So basically, we can switch our directions according to the problem. Okay. So here, positive numbers are on this side and the negative numbers are on this side. So the car location is positive now. Now look at these two figures. So they're kind of same, right? Only difference is my arrow directions are different. So here, this is pointing towards right, and this one towards left. But the car positions are changing, whether it is positive or negative, depending on this direction. So here, the car's location is negative. Over here, it is car location is positive. Here, now the car is on this side. So you can guess what is the position of the car. It is as it is on the negative side of the number scale, because my positive directions goes towards left. The car location is in the negative side. Okay. Now let's look at what is the positive and negative signs for velocity. The previous one is for the position. Now this one is for the velocity. Now here, look at the picture here. The first picture over here in the top left corner. Negative numbers are on this side and the positive numbers are on this side. The car moves from the negative side towards the positive side. Okay. So you can come up with an answer. Is the velocity positive or negative? Then think about the next one. It's moved from the positive side to the negative side. Is the velocity positive or negative? I'll show you the answers, but you can argue within yourself and tell me what is the velocity sign. Is it positive or negative? And in the top right corner picture, the car moves from the negative side to the positive side. and the bottom one, it's moving from the negative side to the positive side. Okay, so in the first one, the car velocity is positive because it started from the negative side and it's below the direction of the positive direction. So it's moved towards this way, right? From the negative side to the positive side, the car velocity is positive. Even though it started from the negative side, it's moved in the positive direction. Then on this one, the car velocity is negative because it's going in the opposite to the positive direction. And on this one, the car velocity is negative because it started from the positive numbers and again, it's traveled opposite to the positive direction. So it is negative. Now here, the car started from the negative numbers and traveled towards the positive numbers, and also it's followed the same direction as the positive direction pointed, right? So the car's velocity is positive. So these positive, negative directions are really important. You can use right, left, or some other directions like south, north. But in physics, when we are calculating it, we say, oh, the towards right is positive. Or you can say towards left is positive. Again, it is convention, but in many problems, you get a defined positive direction. Anyway, remember, when you're taking the velocities, if it is moving in the positive direction, then it is a positive velocity. If it is going opposite to the positive direction, then it is a negative velocity. Okay, so these signs are important when we are moving into the acceleration. All right. Now let's see whether this will work for us. Yeah, see, that's why I put everything into one slide, but it's not working for us. So. Okay. Now let's look at the third term. When we are defining the motion, we need to know about position, distance, displacement, velocity, speed, and the other quantity is the acceleration. So anytime when you're driving, you give gas, right? So to accelerate object. And then when you apply brake, you slows down. It is another acceleration. So we call that as a deacceleration. So acceleration is changing velocity over the time. Okay. So if the speed or let's say velocity, because we are going to define it as a vector quantity. So velocity, the changing velocity over the time is an acceleration. So it doesn't matter whether you are speeding up or slowing down, give gas or apply brake. Both are considered as acceleration. So the definition for acceleration is the rate of change of velocity. So the acceleration can be calculated using this equation, which is final velocity minus the initial velocity divided by the time interval. So basically final time minus the initial time. So here we come with the question whether the acceleration is a vector. Now, if you look at the equation, the time is not a vector, it is a scalar quantity. Because we are not defining the positive time or a negative time. We are not really considering that. So the time is not a scalar quantity, but the velocity, time is a scalar quantity. It is not a vector quantity. Then the velocity is a vector quantity because we know we need to consider the direction, right? So here, when you're calculating the acceleration, you are using the final velocity minus the initial velocity. That means we need to consider the direction, right? So the acceleration is a vector. So that's going to make the life a little bit complicated because we need to consider whether it is a positive direction or a negative direction. All right, again, we're going to use symbols to indicate all these letters like words. Final velocity, without using the whole two words, we are going to use VF to indicate the final velocity. And to indicate the initial velocity, we use VI. And final time, it's TI. And TF because it's final. And the initial time is TI. So you see like this letter IF, that's the initial and final to indicate, right? And V to indicate the velocity, T indicate time, A indicate the acceleration. So if you look at, if you put this one into an equation format, it will be A equal V final minus V initial divided by T final minus T initial. So I know some of you are taking 201 0202 maybe in the future. So in that case, you will be using a textbook, and in the textbooks and the lecture slides, you will see all these equations. But before you going into the equation, understand like what are these terms represents. It's really important. And most of the time in textbooks, they're using these notations according to the word, like initial. So here initial, I is indicating initial, and velocity indicates the V. Okay. So we can use those equation accordingly. All right. So let's do an example calculation. So let's say there's a car which is accelerates from an initial velocity. See the symbol? It's VI, which is plus 10 meters per second. And the final velocity is plus 20 meters per second. Now, velocity is a vector, so this sign is really important. In order to accelerate from 10 meters per second to 20 meters per second, the time taken is 2 seconds. So what is the acceleration? Let's draw a picture. Drawing pictures really helpful in most cases rather than just staring at the sentence here. So I draw a picture. You don't need to draw fancy pictures. You just draw a sketch, right? So here initial velocity is 10 meters per second and the final velocity is 20 meters per second, T initial. So start time is 0 and it's traveled 2 seconds, right? The time taken is 2 seconds. So here I'm going to consider my positive direction to be this side. So that is the second step. First step, you draw a picture and label everything, every known quantities or values. And then the second step is you define your direction. Now here I'm going to define my positive direction towards this side, towards right. Okay, so I define my direction. Now let's apply the equation. So the acceleration, see this little symbol here high above the A, that's indicate that the A is a vector. So if there's a vector quantity, we can use either this symbol or little arrow on top of this. Okay, so acceleration is delta V, that's a change of velocity over the change of time. So it's V final minus V initial divided by the time. Here, the final velocity is 20 and the initial velocity is 10. So 20 minus 10 divided by the time taken. So it's 2 seconds. The answer will be 20 minus 10, which is 10 divided by 2, which is 5 meters per second. You can use a calculator if you're messing up with the numbers. But these numbers, you should be able to do it by without a calculator. Okay, so that's how you calculate the acceleration. Here, there's a little mistake here. Actually, it's a big mistake. The acceleration unit is meters per second squared. Okay, so the acceleration is 5 meters per second squared because here per second divided by another second. So it will be twice as seconds. So it will be meters per second squared. All right, now let's consider a different scenario. So let's say my positive direction is towards the right, but here at the initial time, the velocity is negative 10 meters per second. So the car is really moving in the opposite direction to the positive direction. So here positive direction is towards the right, but velocity initially is negative 10 meters per second. So it's pointing other way around, right? So it's going in the towards left. So at t0, the velocity is negative 10. At t equal 2 seconds, the velocity is negative 20. Basically, it's pointing to the other way, right? That's why it's negative. So it's pointing to the left. Now, negative sign indicates the moving direction is opposite to the positive direction. So it's going other way around to the left. So you can calculate the acceleration again. Now it's a little bit tricky when you're applying to the equation. Here, we know acceleration, which is V final minus V initial over the time. Now V final, let's go see what is V final is. V final over here, it is negative 20. So don't leave that negative. It's really important, right? So take both negative sign and the number and the units as well. So negative 20 meters per second. And then you have minus here. So I follow that equation. So minus, and then V initial. So V initial is negative 10. So I use negative 10 again over here instead of VI. Don't leave the negative in front of the 10 as you have this one. It's not the way to do it. So you need to have this negative that's coming from the equation. And this negative, the second negative over here in front of the 10, that is coming from the definition of velocity. So here, velocity is negative 10. All right, let's solve it. So negative times negative will be positive, right? Negative times negative, it's positive. So negative 20 plus 10, so it will be negative 10. Then negative 10 divided by 2 will be negative 5. Here, negative times negative, it's become positive, right? So I end up getting negative 20. Negative times negative, it will be plus 10, right? And then that's equal to negative 10, right? You agree? Then you take that one and divide it by 2, because time interval is 2 seconds. So here we have to divide this value by 10. 10 divided by 2, not only 10, it's negative 10 divided by 2, that's equal to negative 5, right? And the units will be 5 meters per second squared. Again, I have the wrong units on the PowerPoint slide. Please edit that. This one, this value should be negative 2. Negative 2. It's 5 meters per second squared. Okay? Per, that's why you have a negative here. Per second squared. Okay? 5 meters per second squared. Any questions? Okay, so please edit that one on your notes. The units for acceleration is meters per second squared. All right, so here in summary, so let's say this is the positive direction. In this case, this is the positive direction, and this is initially the car is at moving with 10 meters per second, and finally it's moving with 20 meters per second after 2 seconds. So velocity and acceleration is in the same direction. So here we see that the speed increases, right, from 10 to 20. Speeds increases and the velocity direction is same as the acceleration direction. So the speed, we see the speed is increasing. And then in the second case, we saw that the positive direction we defined in the opposite direction to the motion of the car. The starting velocity is negative 10. The final velocity is negative 20. So the velocity and acceleration in opposite direction. So that's basically a speed decreases, negative 10 to negative 20. So it's kind of you apply brakes or you're going in the opposite, like reversing, okay? So these are the two conditions that you would see in a acceleration problem. This is a very good example about throwing a ball vertically upward. Okay, so let's analyze this motion. So this boy in the picture is releasing a ball from his hand and it's go all the way up, he throw it, right? So it's go all the way up and at the top point, it's come back, okay? So at the release point, if you try throwing something, you basically push the ball, right? After you push the ball, you let it go. So in second later, there's no contact between your hand and the ball. So after the ball released from your hand, there's no contact between the hand and the ball. So there's no force acting on the ball other than the gravity. Only its weight is acting there. So there's no push force that's continue to act on the ball while it is in the air. So once it's in the air, only force acting on the ball is the gravitational force, which is the gravity, which is its weight, okay? And due to the air friction, there might be some force that's coming from the air or the wind, let's say, right? So those are the only two forces can be act on the ball after it's leave the leave the hand. So we'll talk about forces when we are going to the Newton's law. But at this point, what we're going to do is we're going to analyze the speeds, the velocity, and the acceleration of this ball. Now, the ball thrown from the hand, and that is the path it takes, right? So it's go all the way up and turn and come back. And it's passing the kid's hand and went all the way onto the ground. Okay, so you see It goes from here, and at this point it's passing its starting point and then go straight down. Okay? Here, I'm not talking about something like thrown with an angle. I'm talking about something thrown like straight up. Okay, so this is the release point. So the displacement, that is one quantity that we learned. So displacement is a vector. So we need to define our directions, right? So, so this positive or negative value of the displacement is depend on the location. So here, let's say this is the 0 position. So I use the letter Y because it's a vertical direction. So I like to use letter Y. It's up to you. You can say it is X, C, U, anything that you like. But like as tradition, let's say, as a tradition, we say anything that moving vertically, that's Y coordinate. So here the Y coordinate is upward direction, and this is the release point. At this point, that is the location, 0 location, start point. Okay, now something move upward, right? So this ball moves upward, it's going up like upward, passing the release point. So release point is over here, and these are moving upward direction. So it doesn't matter whether it is coming down or going up, it's above the release point. And my definition is anything above the release point is plus displacement. So at this location or at the top point or while it's coming down, the displacement of this object will be positive. Now, after it's passing the release point, it's going down. And that's the release point, which is the displacement is 0. Now it's going down and it's passing the release point, and it is in the opposite direction to my positive defined direction. So these values, like the location of the ball after it's passing the release point, will be negative displacement. Okay, again, in summary, displacement is positive or negative. It's based on the location. So here in this example, I defined my location, the 0 location, to be the release point, and I define upward is positive and downward is negative. So if the ball is above the release point, then it is a positive displacement. If it is below the release point, then it is a negative displacement. Velocity is positive or negative. It's based on the direction of motion. Okay, velocity is positive or negative based on the direction of motion. So here, I define the velocity positive. Now this ball is moving upward, so it is a positive velocity. Now at the top point, velocity is 0, so we don't need to worry about whether it is positive or negative. Now it's coming down. Now it's going opposite to the positive direction, so velocity is negative. Now after passing the top point, the ball's velocity will be negative. It is a negative velocity until it hits the ground. It will be negative velocity. Now acceleration, it depends on the direction of force or the weight. Now here, after it released from the hands of the thrower or this kid, it is in the air, right? Only force acting on the ball is the gravity. What is the direction of gravity? It's always down, right? So the acceleration is always down. According to this definition, downward means negative. So the acceleration will be negative for this definition. But in some points, we can define like, okay, downward direction is positive. Then we will switch all our, the symbol, negative or positive. Okay. Anyway, so in summary, displacement and positive of the displacement, the displacement is positive or negative is depend on the location, and velocity is positive or negative based on the direction of motion, and the acceleration, positive or negative, is depend on the force. So in this case, the weight of the object. So acceleration, any point,
Can I
at
ask
any
a
point,
question?
it's 0. Yes, go ahead.
So the acceleration is always downward because the gravity is always downward?
Yes.
Okay, thank you.
And in this case, we say it is negative because I define like upward direction is positive.
Oh, okay.
So
Thank
here
you.
at every point, you see my animation. So at any point, the acceleration is negative. Because I defined the upward direction is positive and the gravity is always down. Yeah, that's right. Anyone else? Okay, then I'll move on. What time is it? Okay, 10 o'clock. Let's learn about motion diagrams and then do some questions so we have enough time to complete questions. Okay, so motion diagrams are a really important thing analyzing the motion of objects. So in the early ages, Aristotle and Galileo, this is what they did. So they draw the motion diagrams of things. They didn't had any motion sensors or anything, but these days we do have motion sensors which send a beam, a sound beam or different beams, and then we get the reflection and we can detect its motion, like speedometers or the policemen that they're using the speed meters. So they are using motion diagrams, but it's highly advanced technique, right? So they have this, they're not going to do all these calculation manually. They always use this technique that it's automatically calculate things. But early ages, we use these motion diagrams to represent the motions. So here it is a model that we're going to use. Now, if you take a paper, maybe let's try this. So take a paper. Yes, I have a paper here. And I take another paper, which is the same size as this one. Okay, so I have two papers here. Now, if I drop this, it will go all everywhere, right? Due to the presence of air, this will go all the way around in the room. Now, if I make this a ball, so I'm basically changing the shape of the object, right? Here I had a paper, which is surface area is big. Now here I make the same paper, same size paper to a ball, right? Now if I drop this is really straightforward motion. It's straight, it's dropped straight down. So it's very easy to analyze. But this one, it's floating around, right? It's difficult to analyze. We need to define directions, like various directions, and we have to talk about the forces acting on each point. So it's difficult. So we like this model instead of this model. So we call this as a particle model. So it's a paper, but I model it to a particle. I know you will say it is not a particle. Yeah, particle should be really tiny. So for this model, I make it to the shape of a ball, very tiny. I'm not considering the size of the ball. I assume this is a particle. Okay, so I'm not going to consider the radius of this sphere or anything. I just make it a dot. Okay, so this is called a particle model. So when you're drawing motion diagrams, we consider this as a particle. So it doesn't matter whether you are analyzing a motion of a car or a truck. They're really big objects, right? But in our analysis, we just think, oh, this big truck going to be this small model of particle. So we call this as the particle model. So any big object we can consider as a dot, and when we do the calculation, but all the other error factors are coming from the mass distribution. For now, we'll use the this particle model, and let's talk about the motion. Okay, so these pictures, what I'm going to do is I'm going to take pictures of a motion of an object, like at every second, let's say. So we call this as stroboscopic photography. So people use these stroboscopic pictures a long time ago to analyze objects and motion of objects. Still, we are using that. So if you were in the real class, I would show you a stroboscopic photography technique. We have a tiny ticky machine. So when the object is moving, the machine sticks and make a dot diagram. All right, so let's look at it from this animation. So let's say there's a person ran in front of you and you want to analyze it. Actually, there are jobs in regard to police department. They're analyzing motions. When there's an accident going on, they want to see like which one came in high speed and which one came in the wrong direction, or analyze like which one hits the car first, right? In order to do that, they need these motion diagrams. So they take the videos and then they analyze the motion of those cars by using those videos. So video analysis, right? Anyway, so this person ran in front of me. I want to take pictures at every second, let's say. So I don't let him run right away. When he runs, at the same time I will take pictures at every. Right, nice. So I took pictures at every second. I need to define my direction. So I would say, all right, to the right is positive direction as I draw in the dash line here. And the time frame between the pictures is 1 second. So I have taken these pictures at every second. Okay, and this is the starting point. Actually, he started from somewhere else, but I define my 0 position is this location. So I really don't care what happened before this position. So he might be sleeping somewhere or resting. I really don't care. I'm caring about the region that I'm going to analyze. So as I define, this is to be the 0 position for him. Now, after 1 second, let's say he moved 10 meters. In the next second, he moved 20 meters. In the third second, he moved up to 30 meters. And in the fourth second, he moved up to 40 meters. So you see, at every second, he's moving 10 meters each, right? Now here, as I mentioned, I'm going to draw a particle model because if I'm analyzing this person, I can analyze any position, maybe his leg or maybe his nose, right? So any location, I have to pick a location to analyze. Instead of doing that, I will pick a particle model. So I'm going to represent this person as a dot, right? So here, this is a particle model for his motion. And if you isolate this one, this is called the motion diagram. Now, in this motion diagram, I don't see any numbers. I'm talking about this black rectangle. Okay, so these are the dots. So this is the motion diagram. So I don't see any data here, except I see the spacings of the dots. Okay, and I know that I have taken this pictures at every second. So I know the time it's taken to make these dots. So this is called a motion diagram, but specifically I can say that the spacings between the dots are equal. That means this person has moved with a constant velocity. And I know he moved towards this direction, right? So in the motion diagram, this is the direction that the person moved. So he's moving in the positive direction. So this motion diagram represents an object that's moved with a constant velocity. Okay, so we need at least 6 or 7 dots to represent a motion diagram. If you have only 1 dot, we cannot say anything. If you have only 2 dots or 3 dots, it's hard. We can say like, oh, these distance are equal, so it's constant motion. But we need at least 6 or 7 dots to see, like, explain it explicitly. Okay, so we need to analyze at least 7 seconds to see the motion diagram, a complete nice one. All right, now let's put this into a position versus time graph. Difficult, right? Okay, so here I have position on the y-axis, the vertical axis, and on the x-axis I have time plotted. Now here's the grid sheet, and I'm going to draw position versus time. That means position goes to the y-axis and the time goes to the x-axis. Now let's mark the scale on the axis. So here 10, 20, 30, 40, and here 1 second, 2 seconds, 3 seconds, and 4 seconds. Now let's mark the positions according to his motion. So at 1 second, he was at 10 meters. At the 2 seconds, he was at 20. Third second, he was at 30. And 4 seconds, he was at 40 meters. So this is how I mark the data on a graph, right? So I look at the position at each time and I mark it as a dot here. And then I can draw a best fit line. So luckily, these are nicely distributed. So I can directly draw a nice graph here, which is a best fit line. All the 4 data points are on the graph, which is really nice. So this is a constant velocity, right? See, it's a line that has a slope. So it's a straight line with a constant slope. So it is a position versus time graph. So we call this as a graph of constant velocity. Okay, so there's no acceleration. So position is varying constantly over the time. If it is acceleration, it's speeding up, right? So it will be moving 10 meters in the first second, and in the second, it might go to 30 meters. So it's increasing velocity. But this one, he is moving constant 10 meters at every second. So its speed is 10 meters per second, right? So this is a graph of position versus time graph of a person that's moving with a constant velocity. Now let's look at this one. So beginning x0, then 10 meters, 30 meters, 60 meters, and 100 meters. But look at the time frame. It's 1 second, 1 second, 1 second, 1 second. So within 1 second, his motion, the distance that he is moving has increased, right? So he's accelerating, isn't it? That's why he's increasing its gap, right? Now let's look at the motion diagram. Here I'm going to mark dots at every second he is been, and see the spacings of the dots are increasing. I think you can see it from the slide here. See here a shorter distance, but over here a longer distance, right? So this simply describe or represent in a object that's accelerating. So this is a motion diagram of an accelerating object. Okay. Now here, the average velocity vectors can be found by connecting each dot to the next with a vector arrow here. So we can connect these lines with a arrow. So always we are using arrows to represent the direction, right? So again, this is a vector. So we are using a direction to indicate the displacement here. Now, this represents the velocity vector because it's the distance moved by 1 second. And the second one will be the velocity from the second dot to the third dot. Then the third one over here, that is V3, the third velocity of the object that's moving from the third point to the fourth point. And this one will be the fourth point to the fifth point. So it is V4. So I'm using all these symbols, V1, V2, V3, and V4. So those are the velocities at each, between each dot. All right. Now, let's analyze this a little bit further. So here V1, V2, V3, and V4. Now that's V2. If I subtract the V1 by V2, so I come to this point and I subtract V1 from V2. See, like in vectors, we can subtract by drawing the arrow in the opposite direction. So here V2 minus V1, and there's a little gap here, right? That represents the acceleration because that's the change in velocity over time is the acceleration. So this little gap between V2 and V1, that is going to be the acceleration. You can do the same thing here. V3 minus V2. Here, that's the acceleration. V4 minus V2, that's the acceleration. Now look at this. At each point, between each point, the acceleration value is the same. Speed has changed a lot. The velocity is changing, like gaining. But when you subtract the final velocity by the initial velocity, we can calculate the acceleration. So between any of these points, the acceleration is this much amount. Now, if you measure the size of this arrow, it's kind of same, right? So that is a constant acceleration. So this person has ran with a constant acceleration. So it is an increasing velocity in the positive direction. Now let's plot it into a graph, position versus time graph. So I'm going to mark the data points. I'm not going in detail because I already talked about the graph, right? So this is the position and this is the time. So I'm going to plot the graph here. I think you can read it clearly. 4 seconds, 100 meters. Yeah, after 4 seconds, it's 100 meters. In 3 seconds, 60 meters. 3 seconds, 60 meters. In 2 seconds, 30 meters. So in between 40 and 20, 30. And then at the 1 second, it's 10 meters, right? So here, now if I draw a straight line, see, I cannot take all the data points onto the straight line. But if I draw a curve, look at that. When I draw the curve, all the data points are on the curve. Now this increasing position over the time, which gives an increasing velocity over here. Increasing velocity, that's why it's increasing its gap over the time, right? So again, position versus time graph for an accelerating object is a curve like this. Okay, so shapes of the graphs tells us what is the motion is describing. Okay. Now here, if we calculate the rise over run at each point, you can calculate the velocity, the slope of the graph at each point. If you calculate the slope of the graph at each point, that tells us the velocity because it's a position versus time graph, position over time, right? So that's velocity. Okay, now let's try this one. So here I have two motion graphs. Can you describe the motion of blocks? The first one and the second block. What do you think? What is the first block describing? Look at the gaps. Remember that each dot has drawn in every 0.2 seconds.
The first one is acceleration.
Why do
while
you
the
think so?
second- Because the gaps is getting bigger every time, every 2
Yes.
seconds.
Yes.
So it's acceleration.
It's accelerating because the gaps are increasing. Yes, that's right. Then block 2?
It's constant, so it's not acceleration.
It is not accelerating, but it's moving with a constant velocity.
Velocity, yeah.
Yes, yes, that's right. Thanks. So the second block is moving with a constant velocity because the gaps are the same. Here, it's accelerating because gaps are increasing. Every 2.2 seconds, the gaps increases. That means it's accelerated. Now, do the blocks ever have the same speed?
Yes? Oh, no.
Can you
Yeah,
repeat
in
number
order to
5?
do that, you need to see the gap, like wherever. Do we see the same gap of the first block, like this distance somewhere here? No, right? This distance is not there. Then this distance, the distance between 2 and 3, that length, do we have anything that match with that? Then you see 3 to 4, there's a gap, right? So from here to there. So you can read these numbers and see the value. So let's count 1, 2, 3, 4. So there's 4 scale lines. So let's see this one. 1, 2, 3, 4. 1, 2, 3, 4. Yeah, see 3 to 4. 3 to 4 on the block 1. If I start from this edge of the block, then I have 1 block, 2, 3, and 4, right? And then if I go to the second block, 3 to 4, I have 1 gap, 2, 3, 4 gaps. So at 0.2 seconds, first block has moved 4 gaps, and the second block also moved 4 gaps. So that means it has the same velocity because it's moved the same distance over the same time. Then let's look at 4 and 5. So 1, 2, 3, 4, 5. Here it's moving only 4 distances, right? So 4 to 5, block 1 moves more distance than the second block. So from 3 to 4 on the block 1 and 3 to 4 on the block 2, they are maintaining the same velocity because their distance moved over the time is the same. But every other place it does not because block 1 is accelerating. So it's increasing its speed at every point. All right, so it's 10:20. Let's go to the top pad and do a couple of questions. And if we have time, we'll come back and continue about the graphs. Oh, I should have taken your attendance, but it's okay. Please send you.
Hello.
Yeah, hello.
I just need to put in the attendance code. Was it 186 something else?
I didn't open the attendance yet.
Oh, okay. I saw the code. That's why. Sorry.
Okay. I think I didn't open.
Yeah, you probably didn't
Yes.
open. It probably was just showing. Sorry about that.
Let's do this question.
Mm-hmm.
And then I'll take the attendance because I forgot. Can you see the question on the screen or on your?
Yeah, we can.
Yeah, we can.
All right, so I'll stop counting your responses. Okay, let's look at your answers. Yeah, that's right. So acceleration means changing velocity with respect to the time. The velocity need to change to get an acceleration, right? Changing distance with respect to the time, that is the velocity. The distance over time is the velocity, or yeah. And the product of velocity and time, no, we didn't learn anything about that. Velocity times time, it's ms, that's give you the distance. No, product of velocity, product of distance and time, C and D are not possible at all. So those who answered, I have 9 of you saying product of velocity and time. We didn't talk anything about product between velocity and time, right? So we are always talking about like how the velocity or the distance is moving over the time with respect to the time. Yes, so the correct answer is A. Okay, now let's take attendance. I'll minimize and keep open, and then we'll start the next question. All right, I think I can stop counting the answers. Almost all of you have answered. Okay. Yeah, nice. Very nice. Okay, so when you're trying this type of problems, some of you might just look at the numbers and take 20 divided by 5. Yeah, you will end up getting a correct answer because this is a very simple question. But the way that you should do it is you should write the equation, which is acceleration equal v final minus v initial divided by time. And then you go ahead and look at what is v final. So what is v final? So here v final is 20 meters per second because that is its reaches to, right? So v final will be 20 meters per second. Now, V initial, what is the V initial in this problem? Then you go see what it is tells you. So it started from rest. Rest means it's starting with 0 speed, right? So it will be 20 minus 0 and the time taken is 5 seconds, right? So that's how you should do. For this problem, if you look at just the number like 20 and divide by 5, you will end up getting the correct answer because the initial velocity is 0. But if you have different numbers, then you should use your equation, especially when it's got negative directions. Then the life will be a little bit complicated. But if you're using this equation, you should be good. Okay, let's see. I'm going to stop counting the attendance. I think all of you had time to send the attendance code. Yeah, that's the correct answer. And one more thing, you need to look at the unit. So all these 4 answers came with the correct unit. So unit does not affect that much on this answer. But remember, look at the unit. It's acceleration, so it's meters per second square. Okay, now we are going to look at your responses. Okay, so 16 of you got confused by something. How do we do this calculation? So acceleration is V final minus V initial, right? So here V final is 10 meters per second. V initial is 5 meters per second. It started from 5 meters per second. And then it reaches to 10 meters per second within 5 seconds. So it should be 10 minus 5, which is 5, divided by 5. So it is 1 meters per second square. Anyone who answered anything other than C, do you have something to share with me, or tell me something, or you want to any place that you got confused? It looks like to me, those who answered A, you take 10 and divide by 5. No, that is not the way to do it. You need to take V final minus V initial, divide by the time. Okay. Anyone with questions? Okay, let's try the next one. Why doesn't it do it? Okay, good. Oh, D, it's a negative here, okay? Sorry, it's negative here on the D answer. It's not a dot, it should be negative. All right, so let's look at your responses. Yeah, still I have a good portions is giving me the correct answer, so that's great. So the answer is minus 3.5 meters per second All right, so I'm going to write over here. So acceleration, this is the definition. Acceleration is V final minus V initial divided by the time interval. Now, let's see what is V final here. V final is 10 meters per second, right? It's 10 meters per second. And the V initial is 45 meters per second, right? And then the time interval is 5 seconds. Right? Do you agree? And then 10 minus 45 is minus 35. Then you divide it by 5. Sorry, 10. Time taken is 10 seconds, isn't it? I'm sorry. Tell me if I make a mistake. So the time taken is 10. So the value will be minus, that's important, minus 3.5 meters per second square. I can use this because I don't have superscript on this writing pad. Right, so that's how you calculate it. Here, basically, it tells you like it's something that maybe you applied brake, right? It started from 45 meters per second and reaches to 10 meters per second. You might feel like it's not really accelerating. It's deaccelerating. That's true. It's deaccelerating. It's a negative acceleration. So here we ask what is the acceleration? So it should be negative 3.5 meters per second squared. So I have 62 of you say the correct answer, but I still have that portion like earlier, remember, like I had about 20 students who gave the wrong answer. Now it's increased. It can't be. So please use the equation and apply the numbers here according to the equation. Then you calculate it. In the homework, it will give you good practices, but I have a couple of attempts. So you basically like randomly picking answers. I'm not talking to everybody. I'm talking to some of you. So don't do that. Try to use the equation and learn it. Okay. So I'm going to open a very short assignment today for homework, and let's see how you do it. All right, so let's see the other question. Yeah, those who answered 5.5, I think you are adding two numbers. Why do you add? Why doesn't it okay, so slow? Let me clear the writing. Okay, here you go. All right, so this is a motion diagram. So the pictures were taken at every 0.1 second intervals, and ball moving left to the right is the ball accelerator. Okay, so it's a very straightforward question. So let's look at your responses. Yeah, still I have only 62 of you giving me the correct answer. So there's a group, about 20 or 22 of you, it's not really getting this concept. So you need to read the PowerPoint slides and learn it again, okay? So here, you basically what you're doing is you look at the gap between the dots. So here the gap's roughly the same, right? You just eyeball it. You're not going to use a ruler and measure it. You just eyeball. So here the distances are equal. So there's no acceleration. It's moving with a constant velocity. It's moving to the right. It's moving with a constant velocity. We can say that by looking at the picture. So the correct answer is B. Okay, here there are two motion diagrams for particle A and B, and the time intervals are 0.05 seconds intervals of two balls, and it's moving from left to the right. Do we have any of these balls that's accelerated, or are both of those are accelerating? We consider the negative acceleration as acceleration. So slowing down or speeding up, both means acceleration. So what you're going to check is the gaps, okay? Okay, let's look at your responses. Okay, now my good portion went down. Let's see. So both balls are accelerated. Now, as I mentioned, the acceleration means it can be a positive acceleration or a negative acceleration. So positive acceleration means it speeds up. The negative acceleration means slows down, right? So here, if you go to this diagram, and if you measure the distance, like just eyeball it. So here's the distance it's moved in the beginning, and then later in the second time interval, and the third one. So these are the distance it's moving, right? So it's, as you see here, when it's come to the later time, the gaps increased. So A is accelerating because it's changing, it's increasing the gap between the motion diagram dots, right? And then if you go to B, here a larger distance, but here it's shorter distances, right? Coming closer to each other. So it's slowing down. That's why the distance it moved in every 0.05 seconds get smaller and smaller. So this one is negatively accelerating. So it is a negative acceleration. So both balls are accelerating. The ball A is positively accelerating, ball B is negatively accelerating. Does that make sense?
Yes.
Yeah.
Yeah.
Motion diagrams are really nice technique to use. Now I think I have lots of your nursing majors, right? So you might do some physical therapy trainings. I don't know, it depends. And also if we have exercise majors, when you're working with clients, you will be checking their motion. So you're not measuring their whole body motion, but you will be judging you're analyzing their leg movements or hand movements. So this is a technique that you will use, but you're not going to take a camera and take pictures at every second. But the machine that you will be using, use this technique. So when you are using these machines, you know, like how does it function, right? I'm not going to teach you how those machines are functioning, but when you are taking other classes, like in the next year, you might learn about these techniques, okay? All right, so let's see whether I have any other questions listed in there. All right, so let's look at your responses. It's 10:42. So. Yes. Stethoscope. Who says that? Raise your hand. Stethoscope. Who uses stethoscope to measure the falling object? Maybe a falling heart or something. Microscope. That is to enlarge the small object, like you're using an optical device. Kaleidoscope. That is a really cool device that maybe when you're kids you might have used it. So it is a like a triangular shaped tube with made out of mirrors. You can put some objects inside and then you can see nice patterns in there. You can Google it, the kaleidoscope, and you may see pictures in there. So there are toys that uses kaleidoscope. Yeah, so we are using stroboscope to do the motion analysis. Stethoscope, come on. All right. All right, so it's 10:42. So I'm going to call the end of the week for physics class. I will open a very short homework tomorrow, and it will be due before the next class because it's going to be a very short one. Just analyzing, like just reviewing the stuff that we did for Tuesday and Thursday. Okay. All right, so I'll see you on Tuesday.
Thank you.
Thank you.
Yeah, if you have any questions, stay here.
Thank you.
Thank you.
Yeah.
Thank you.
Yeah, sure. I'll see you.
For our next exam, since we're using the lockdown browser, will we be able to use our handwritten notes as well or no?
Can you give me a couple of days to decide, because I am working on to see, like there are some people who doesn't have ID cards or anything, so I'm still making plans, but I'll let you know soon. Okay.
Okay, thank you.